Hello, I'm Mr. McBrien. This is SPH3U, Conservation of Mechanical Energy, or the Forever Ball. A quick glance at the Ontario curriculum gives us a couple of learning goals of interest today. The use of the law of conservation of energy to solve problems involving work, gravimetric potential, and kinetic energy, and describing energy transfers and transformations, and explaining them based on the law of conservation of energy. And that's what we'll cover today. A little more briefly, we're going to discuss the law of conservation of energy and apply it to some familiar problems from our kinematics unit. Okay, so let's start with gravitational potential, something we've already talked about. An object of mass 3 kilograms is suspended at a height of 12 meters above the ground, and we want to calculate its gravitational potential energy. Piece of cake. So our mass is 3 kilograms, our height's 12 meters, familiar g of 9.8 meters per second squared. E equals mgh. Not a problem. So, a couple of seconds with a calculator, and we get that our gravitational potential energy is equal to 350 joules. Not a problem. Okay, what about the kinetic energy? So, again, our mass is 3 kilograms. Our velocity is 0 meters per second, right? Because it's suspended at a height of 12 meters. So, it doesn't matter what our equation is. Our energy is going to be 0 because our speed is 0. So, what have we got? We've got a gravitational potential energy of 350 joules and kinetic energy of 0 joules. Now let's change the game. So we drop the object, and we want to know the speed of the object when it hits the ground. So our v1 is 0 meters per second, acceleration 9.8 straight down, our distance 12 meters. And using our equations from the kinematics unit, v2 squared equals v1 squared plus 2a delta d. v2 equals the square root of v1 squared plus 2a delta d. Substitute in, and we get v2 equals 15.3 meters per second, rounded to 15 meters per second for significant figures. No big deal. Okay, now here's where it gets interesting. Now we've got kinetic energy, and we can calculate that. So we have a speed. We're going to, since we're going to keep comparing these numbers, we're going to keep an extra significant figure here. Our speed is 15.3 meters per second. Our mass is 3 kilograms again. Kinetic energy is a half mv squared, as we know. Substitute in, and our kinetic energy is 350 joules. What about the gravitational potential energy of the object? Well, when it hits the ground, our gravitational potential energy is 0 because h equals 0. So what have we got? We've got a gravitational potential energy of 0 and a kinetic energy of 350 joules. The exact opposite of what we started with. What's that mean? Our energy has been entirely transformed from gravitational potential energy to kinetic energy. But the total is still the same. It's still 350 joules. And actually, this is an illustration of our huge concept for today, conservation of mechanical energy. This key concept is really pretty simple. If we don't do any work on an object using an outside force, the total mechanical energy of the system is going to remain constant. And we can put this in mathematical form, and this will be useful for later. At time 1, our gravitational energy, potential energy, plus our kinetic energy is equal to the gravitational potential energy plus the kinetic energy at time 2. And that applies for time 3, time 4, time 5, as long as we don't do work on the system. So how can we use this practically? Well, we can consider this problem, one that we've studied before. An object's launched from the ground with a velocity of 12 meters per second up. Find the maximum height of the object. And we did this. Again, we did this in the kinematics unit. So V1 equals 12 meters per second, H1 equals 0 meters, V2 equals 0 meters per second. What is the height? And we could do that based on our equations, but there's a simpler way to get this answer. And the other way doesn't illustrate our key concept for today. So let's start with our law of conservation of energy. And then we can substitute in. And we're going to do a little bit of speed things up a little bit by noting that when we started, our gravitational potential energy was 0 because we're at height 0. And when we finished, because it's at the maximum height, speed equals 0, which means the kinetic energy equals 0. So we can simplify the equation to be 1/2 mv squared equals mgh2. But notice that mass is on both sides, so we can divide both sides by mass and get a much simpler equation. 1/2 v1 squared equals gh2. And we can further simplify that by dividing both sides by g, and then by rearranging slightly, we get the height, the maximum height is equal to v1 squared over 2g, a much simpler expression than we used in our kinematics situation. And then we can substitute in for v1 and for g and get 7.3 meters with some very simple arithmetic. Okay, so we talked about this system conserving energy at all times. Now, does that really make sense? Anybody who's bought a Super Ball and tried to keep it bouncing forever will realize that that doesn't quite work. Energy is never transformed with 100% efficiency. If we drop a ball from a given height, it can't bounce back up to the same height because we lose energy to the sound of the ball bouncing and to the energy warming up the floor and the ball. We always lose some energy. It'll be heat, it'll be sound, it can just simply be moving air around. But for most problems that we're working on in grade 11 physics, we're going to ignore that, and in fact we can get pretty good results for a lot of the things we do while we neglect those losses. Okay, so let's apply some of these concepts that we've learned today. Please read pages 236 to 240 of the textbook. Do the problems there, then read page 250 to 253, and do those problems on page 251. Thanks very much, and have a great day.